Welcome to The Explainer. Today, we're looking at something you have almost certainly seen on a plane, but maybe you've never truly noticed what it's doing. Commercial aviation is just an absolute marvel of human engineering, but it operates on a mind-boggling scale of resource consumption. Every single day, thousands of commercial jets burn millions and millions of aviation fuel just to keep us connected across the globe. But what if I told you that one of the most significant revolutions in aviation history, a change that drastically slashed that massive fuel consumption, comes down to a tiny, almost imperceptible design tweak right at the very edge of an airplane's wing? Today, we're going to solve the detective story of the 5% fuel mystery.
Section 1. The Fuel Efficiency Challenge.
Okay, let's dive into this. Pushing hundreds of tons of metal through the sky means even a tiny fraction of a percent of drag reduction can completely dictate an airline's profitability. On modern passenger jets, you've probably noticed that the tips of the wings bend upward. So our central mystery today is how this seemingly tiny vertical extension, a winglet, solves a massive physics problem, reducing total fuel burn by a crucial 3 to 5%, depending on the length of the flight and the type of aircraft. Now, 5% might sound like pocket change, right? But let's scale that up for a second. When you're talking about global airlines spending billions of dollars on aviation turbine fuel every single year, a 5% reduction translates to absolutely massive operational and cost changes. We're talking about millions of dollars saved per airline per year. And it goes further than that. The capacity of an aircraft's fuel tank, its payload, its entire flight range, all of that is dictated by these efficiency numbers. But to actually understand how a little piece of metal at the wingtip saves all that fuel, we kind of need to understand the forces at play. Section 2. Balancing lift and drag. So, to understand the wingtip, we first have to recognize the constant compromise that's happening across the entire wing. During takeoff and landing, high lift devices like flaps intentionally increase the surface area, which creates drag on purpose just to keep the plane airborne at low speeds. But up at 35,000 feet, the flaps are totally retracted. The aircraft needs to be aerodynamically clean, because at cruise altitude, drag is your ultimate enemy. Now, what's really interesting about this slide is how the wing physically morphs for these conflicting requirements. Look at the top profile for cruise. It's super sleek and streamlined. But in the takeoff and landing profiles right below it, the wing fundamentally changes its camber to essentially scoop the air. Yet, even once those high lift devices are tucked away safely for cruise, there is a hidden source of drag that a traditional flat wing literally can't escape. Section 3. The problem of wingtip vortices. And here is that invisible culprit ruining your high-speed cruise efficiency. As the wing generates lift, the high-pressure air underneath naturally wants to escape to the low-pressure area on top. Makes sense, right? Well, the easiest place for it to do that is right at the wingtip. So as it spills over, it creates this swirling tornado trailing behind the plane. These wingtip vortices alter the airflow over the entire wing, creating what's called a downwash. Just imagine an invisible, heavy anchor made entirely of swirling air, constantly pulling the plane back, forcing the engines to burn excess fuel. Section 4. The wingspan dilemma. So, you might be wondering, if the wingtips cause this drag, why don't engineers just build endlessly long wings to push those tornadoes further away? Well, you face two severe real-world constraints. First, increasing horizontal span drastically increases the structural weight, requiring heavier internal reinforcements. And of course, heavier planes burn more fuel, which defeats the purpose. Second, there's a logistical nightmare: standard airport gates. If a plane's wingspan is too wide, it simply cannot park at the terminal. Section 5. Why winglets save fuel. Engineers were totally stuck between a rock and a hard place, which led to a surprisingly elegant innovation. And this brilliantly illustrates that journey. Tracking the roadmap between the 1980s and 2010s, we see the transition into winglets and rig tips. By folding that horizontal extension upward, the winglet acts as a physical barrier. It diffuses that swirling air and weakens the vortex. By mitigating that downwash, the engines don't have to fight that invisible anchor anymore, directly yielding that massive 3 to 5% reduction in total fuel burn. Let's move on and see how this builds. Today, you'll generally see two variations of this solution out in the wild. Traditional winglets tilt upward, perfectly solving that gate spacing issue while delivering that crucial fuel reduction. Alternatively, newer long-range aircraft use raked tips. These are swept-back, highly streamlined horizontal extensions that provide similar drag reductions, but they're reserved for planes operating at larger airports equipped for wider spans. Honestly, both are just absolute masterclasses in mitigating induced drag. Section 6. Environmental and economic impact. Shifting our perspective from microengineering to the macro-scale impact, what does that 5% efficiency actually mean for the world? So the crucial point is this. The impact isn't just financial, it's profoundly environmental. For every single ton of aviation fuel saved by these aerodynamic improvements, we eliminate roughly 3 to 4 tons of CO2 emissions. To put that into perspective, multiply that by thousands of commercial flights daily, and that little upward bend is responsible for preventing hundreds of millions of tons of carbon emissions.
It's a pretty powerful reminder that in the world of high-stakes aerodynamics, tiny structural changes can literally alter the global landscape. The next time you're sitting in a window seat, looking out over the clouds, take a moment to look at the tip of that wing. It's not just an aesthetic choice. It is a highly engineered shield, constantly fighting invisible tornadoes of air, saving millions of gallons of fuel, and protecting our environment mile by mile. Will you spot the invisible engineering at work on your next flight? Thanks for joining us on this explainer, and keep looking closely at the world around you.